Okay. Well, given the fact that it's 5:05, I think it's safe to go ahead and start. Uh, just a reminder, we are recording, which is why we've asked everyone to mute their mics. We'll have a Q&A session at the end, so I'll stop the recording when the presentation's done, and we can talk if you have any questions about today's content. But yeah, so I guess we can go ahead and get started. Will, unless you have anything else to add.
The only thing I would have to add is I'm still using the OBS camera. All right, there we go. I'm sending out emails, and I should have sent out an email with a link to the playlist for our videos of this course. If anyone did not get that that's here, feel free to email me or ask me in the Q&A, and I will get you sorted out.
Cool. So, this is week 3. So today we'll be talking about PID control. We were supposed to be talking about it last week, but we figured we'd take a nice break, give everyone, let them have their Thanksgiving, so that way, when FRC starts, they can know life like everyone else. So this course, we designed it to be 6 weeks. We might cut it down to 5 because we don't want to cut into everyone's Christmas breaks, but we'll, see what happens when we get to week 6. But right now we're on week 3, so last week we'll cover dashboards and logging, looking at advantage scope and things like that. Today I'll be covering PID and advanced motor control. Next week we'll be covering swerve drive. I think we'll be focusing on YAGSL, so if you're interested in that, please come back for that. And then I'll be covering vision and localization in week 5. So I'll be looking at limelights, and then some open source stuff. And then if we have some time, which I want to make some time for, the new QuestNav stuff, which I think is going to be really powerful this year. And it's cheaper than Limelight, so if you're just getting into vision, I would suggest going ahead and buying the Quest system for that. But, we can save that for week 5. And then week 6, if we have time, getting into Path Planner and autonomous navigation with some of the more advanced vision-based systems. But we're talking about PID this week. So, a little bit of an overview of what PID entails. Specifically, we'll be looking at control systems, feed-forward and feedback loops, PID control loops, and then we'll be looking at some of the more advanced stuff that FRC and WPI library has to offer, like trapezoidal, motion profiling, and tuning parameters. So if you're just joining this week and you're new to programming, I suggest watching, but also go back and watch week 1 and week 2, because those are a good introduction to what we'll be talking about this week, because I'm just going to skip over a lot of that stuff. So if you're new and you don't really know how to program, you might be a little lost, but, all the code's going to be on GitHub. It's all going to be recorded. You can just watch back as well. So, control systems. In a lot of mechanical systems, the humans don't really have direct contact over what's happening on the output of the system, right? And so what we have are instead control systems or control loops. And so the human provides interference in the control loop, but they're not directly driving the output of the system. And we do this because we want advanced control, and we want everything to be reliable, repeatable, and precise. So the same thing that we use in industry, we use a lot in FRC. So you have things like input reference. So this would be like your set point, or your sensor input, things like that. You have the feedback or the error, so what your current sensor value is reading and how far off that is from where you want to be. You have the controller, which is the mathematical function that's sort of handling all of the math to get to where you need to go. And then you have the process or the plant. And so this is what you're operating on, right? So this is the motor or some, sort of actuator. And then you have the output, which is what the motor moves to, or what we're pushing the motor towards, right? And so with a control system, you're essentially creating a mathematical model of your mechanism. So we can use this model to predict what we need to do in order to get to a certain output, or to adjust for any measured errors that our model is inputting from all of our different sensors. And so we can have a bunch of different sensors. Encoders are the biggest ones, and we'll be talking about those. But yeah, you could have a lot of input into your, model. So the first sort of control system that we're talking about is the feed-forward controls. And so when you have a mathematical model of your robot, right, you can use a feed-forward control loop to sort of estimate what you need to get to a certain position. So an example of this would be like, let's say you're driving on carpet. You can use feed-forward control to sort of provide additional input to your drivetrain to overcome static and friction, right? So like static friction. So this would basically be like a little boost that you give to your joystick input to reduce the error that it comes from like having your motors to overcome the static of driving on carpet. This is called open loop control because there's no sensor feedback. So this is using straight physics-based estimation to figure out what you need to overcome some sort of obstacle. Another big thing is gravity compensation. So elevators were a big thing in this last year's competition, so I'll be coming back to elevators a lot because they're a excellent example for control systems and advanced control systems. So in an elevator, you can use feed-forward control to compensate for the gravity that's affecting on your system. And so how this would work is you would basically drive your elevator up to a certain position and then give it just enough voltage, give the drive motor just enough voltage to where it's not dropping due to the weight on the elevator mechanism. And so that would be sort of an example of feed-forward control overcoming that, natural gravity that's pushing on your system. The next one, and probably the most powerful in FRC, is what we call feedback control. And so this idea is we want to correct for errors in the system, and so we compare a desired state versus what we're actually at, or a measured state. And so there's a lot of ways that we can measure a particular state. Like I said, the biggest one are encoders, and so these are essentially sensors that you mount on a motor shaft or something that spins, which translates to motion. And so you can measure the rotations of that shaft or that axle and figure out, distance based off of that. And so this is great for feedback control, especially in, we'll go back to the elevator system. You can convert those motor rotations into elevator height. And so you can say, hey, I want to be at, 3 feet high. I don't know how high that is. But your feedback control will say, okay, well, we're at 0.5 feet. We need to get to 3 feet, so we'll apply X amount of voltage to our motor, right? And so some common examples of this, because these are used everywhere: cruise control, temperature-based things like an oven or your thermostat. They're used all over the place, and they're very powerful on FRC, especially for autonomous, but they're really good for teleop too. And so what you get is a system that actually self-corrects, right? So when an FRC or robotics team is first starting, they'll often start doing time-based autonomous systems, which is fine, but you have a lot of external factors that can affect, the timing of things. So you would measure to get 5 feet, I want to drive for 3 seconds at X amount of voltage. When you use a feedback control with encoders, you can account for all of those external factors that can influence the performance of it. So battery sag, friction, someone kicks your robot, something like that. And so one of the most common methods of doing this in FRC is what is PID control. Did I skip? Oh wait, no, I didn't skip. Sorry. This is just a jarring transition. And so what we'll eventually work towards especially with the elevator, is a combined control loop, right? So you take feed forward function and feedback function, and you create one advanced control loop. So the feedback is measuring your current state, measuring where you need to be, and applying, the right amount of output to get to where you want to be at. The feed forward loop can help the feedback loop and make it more reliable and make it more, dependable by compensating for gravity, compensating for friction, so it reduces the work that the feedback controller needs. If we get to Path Planner, we'll talk about how important feed forward is, especially when you're doing navigation things, because over time static friction can impede the accuracy of your system. So this is just something to keep in mind. So PID control. PID is a feedback controller that tries to adjust the output of your mechanism based on the past error, the present error, and the predicted future error. And so PID stands for proportional, integral, and derivative. And so these are three parameters that you're tuning for your control system to get to where you want it to be. And so I've got a couple examples of what the PID sort of control loop looks like on the right here. Hopefully you can see my mouse. But this blue line up here is where we want to be, or the target output, or the target state. And this red line is where we're currently at. And so by tuning those three parameters, you can find this optimal little green line right here to get from where you're currently at to where you need to be in an optimal manner. And so tuning a PID controller takes a little bit of time, intuition, and just experience. So the proportional term is essentially what most of your time will be spent tuning. It's the most important one. But essentially this is just a multiplicative term that pushes you towards the target. And so this red line indicates an underdamped system, and so there's a lot of oscillation. This indicates a very high p-value. So you want to pull back on the p-value a little bit if you see something like this. So what this means is you move quickly towards your target position, but you overshoot, and so your system tries to self-correct it and overshoots again and again and again and again, and so on and so forth. This yellow line represents a proportional value that's a little too low, and so it will eventually get there maybe, but it's not optimal, right? And so the integral term, you don't really have to worry about it. Most of the time it's pretty much zero. There's not a whole lot of time when you use a non-zero integral term, but essentially this eliminates very small steady state offsets, so things that can impede over time. And then the derivative term is sort of a way to damp this oscillation. So if you think that the green line is not quick enough, then you could increase your P and also increase your D. So there's a lot of cool ways to tune it. There's actually, let me pull up, FRC has or WPI library, I guess, has a fun little tuning simulator in their documentation that you can just play with. We can link that in there. Yeah, right here. So, whoa, okay. So right here, we're using PID for velocity, right? So in their little simulator, they have a flywheel, I think that's what it's called. Essentially, it's a shooting mechanism, and so you have the motor RPM where you want to be at, and you have your kV value. So if you set it to 10, right, that is really high. Let's set it to 5, right? But yeah. So these are the different methods of, feedback. This is sort of a basic feedback system with one value. Here is the PID, so you have 3 or 4 different ones. So if we set it to like 10 again, here we have that oscillation. So P is obviously way too high. So if we set it at 5, yeah, that's still too high. I haven't played with this one. I think I played with the elevator. The elevator one. So yeah, they have a whole bunch of cool whoops. They have a whole bunch of cool PID tuning experiments that you can play around with. But I want to show you how to do that actually in FRC, right? So tuning the 3 parameters, you want to find the optimal balance of speed, stability, and accuracy. So you've got, oscillation. Is that fine? There are some cases where a little bit of oscillation is okay. There are some cases when it's absolutely not okay. Like if you're using an elevator and you have a mechanical limit, you do not want to oscillate and break something. But, it's case by case, right? So I am going to bring over some code, and we're going to code a very simple PID from scratch. So I'm going to zoom in here. So this is all stuff we talked about in first and second week, but I'm just going to create a new command-based Java programming. So there's 2 things. You got the command robot and the command robot skeleton. The only difference is the command robot comes with a lot of boilerplate examples. I'm just going to click the skeleton because otherwise I'd have to delete all of them. And then I'm going to, here we go. I got a lot of PID stuff in here. I'm going to say week 3 PID right here. And then I'm going to put the project name. And then I'm going to put my team number, which is 4523. Shameless plug. Okay, so code generated. And so with PID, what you'll typically have is you'll have some sensor and some output, like a motor and an encoder. I do not have access to those, so I'm going to simulate everything. But everything translates the same, so all the libraries are very similar, and all of the sort of tuning schemes are very similar. And I would recommend playing around in the simulation first before doing anything mechanical, because there's a lot of nuances with actually programming it on a robot. And I'll walk through those at the end or after this, but yeah. So I'm going to pull up the robot container, and then since this is the skeleton, I didn't generate any commands or subsystem folders, so I'm going to make my own commands and subsystems, and then I'm going to pull up right. So the subsystem, we're going to just call it simple PID. And so the goal of this subsystem is to essentially simulate what an output of the mechanical system would look like. So I'm going to have 2 class variables up here, position and velocity. And so I will be updating both of these based on PID controller output, right? And then I'm going to make my constructor, which is, I'm just going to do simple PID. And then, yep, that's it. And then I'm going to have my PID controller class. So the PID controller is a class that WPI library basically or the WPI people made, and it's essentially a basic PID controller loop. And so how to create a new one is you would just call it, like, let's say I'm going to call it just controller1 equals new PID controller. And so there's a couple ways to instantiate it. This one, you have to give it a P, I, and a D value. So I'm just going to give it initial values of 1, 0, and 0, right? I mean, just random values. And then, let's say you want to tune your system on the fly. So we'll be using sort of what we learned last week with dashboard and logging. I'm going to be pushing all of these numbers to the smart dashboard so that way we can change them and see what they have to happen in real time. So smart dashboard is just a class. I think it's going to be deprecated, but it's a pretty easy way to publish things to the network table. And then we'll use the smart dashboard to push things onto the network table. And then we'll use other dashboards like Advantage Scope or Glass to play with them in real time. So that's sort of the, I guess, foundation of all of these. It's just the network table. So we're going to put our number, and we're just going to put controller1 / KP, and then we will give it, actually need to do this. I need to make these variables that I can change. So we'll do 1, 0, 0. And then I'll change these to KP, KI, and then KP. And then with this put number, I'll put my KP. And then I will copy and paste that and change it. Boop, boop. Right? And so with this, I'm just publishing these 3 numbers to the smart dashboard so I can read them later. And then I want to have a final value, which is our target position. This could be target position. It could be, we're doing position for a lot of these, but you can just swap velocity. Like if you want to use this for like a shooting motor and you want to keep a constant velocity, this will all transfer over. But I'm just going to use position because that's, I feel like, the most, I guess, useful. I'll just put it to 5 right now. Right? And so, hold on, move this out of the way. Whoops, sorry. Okay. Right, so this is our, and we'll push that target position also to the network tables, because I want to look at that one too. Cool. So we'll go ahead and periodic. So we'll make our periodic function, which is just going to run at 50 times a second, right? Or one of the two. Okay. But it's going to run continuously during teleop or autonomous, wherever is using this subsystem, right? So what we're going to do is, since we want to change our PID controller, their constants on the fly, we're going to add these. So we're going to change PID constants based on network table entries. And so what we'll do is we'll do controller1.set P, right? So we can change the P constant, and we're just going to set that to whatever number is in the smart dashboard. So we'll do controller1 / KP. Oh, what the heck? KP. Yes. And then we need one more value, which is just the default value. So what this is going to do is it's going to, every time the periodic, and I don't recommend doing this in competition. I recommend tuning it outside of competition and then, having these set in your constants file, but just for fun, we're going to do it here. And so every time this loop comes through, we're going to check to see if a new number is input in the KP slot in our network table, and if so, we're going to change our controller1 PID controller to have that value, right? And so then what we're going to do is we're going to calculate the output of our controller, of our PID controller. So we'll calculate, and then we will base it off of our current position, and we will base it off of our target position. So what this function is going to do is it's essentially going to take your measured state and your target state, and it's going to take those three constants, and it's going to calculate the output that you need to essentially get to that state, right? And so in a real system, what you would do is typically you'll, like, let's say you're measuring in raw encoder units, and let's say you're working with the elevator. You would want to first convert your sensor units to some known common value. So let's say it's like meters, right? You would want to see how many rotations is 1 meter, and then have that as a constant that you can convert your sensor units to meters. And then you'll want to convert the output, which is going to be in essentially like a velocity, to something that your motor can read, right? So I'm going to show how to do that later. So we have this output, and then we're just going to simulate adjusting our motor's velocity from this output. So times 0.1, and then we'll update our position based off of this velocity, right? So velocity times 0. Boop, boop, boop. And then we're going to dampen this. 0.9. Oh my goodness. And then one last thing is we're going to publish our position to the network tables, and then we are going to publish our error to the network tables. So we'll do target position minus output. Okay. And so essentially what this line of code does is it's like your conversion. So you're converting whatever your PID controller outputs into velocity, and then this is like simulating applying that velocity to your motor. You can also convert it into volts, so you can convert your sensor units into like raw volts. So like let's say you want to run it at half speed, you would convert it to like 6 volts, and then you would send that to your motor, and the encoder would get the new position. So this is just a simulated version of that, and then we can publish that out there. And then I'm going to put a couple of functions in here, so I'm going to clean this up so you can see. Alright, so we'll have one function, we'll do set target. Oop. And so all this function will do is it will take in a number, and it will say target position equals the new target. And so with this, we can update the target position of our PID controller, and then we'll have one more function, reset, in which we can zero everything out. So we'll zero our velocity, our position, and our PID controller. And so we want to call reset on this because the I and the D are both time-based. And so every time it's called, it's sort of incrementing this time-based system. And so we want to make sure that we reset it when we reset our position and velocity, because otherwise it's going to be thinking that a lot more time has occurred. All right, because I mentioned that this I value has more weight the longer an error is. So, okay, so we've got a basic subsystem. Now we're going to go to our robot container, and we are going to, we don't really have to do too much. We just have to make a new instance of it. So we'll say private final PID subsystem. Or what did I call? Oh, simple PID. Right. What? Float expected. Hold on a second. Simple PID. Oh, duh. I have to name it. Okay. And then we want to configure bindings. Right. So I'm going to have 3 functions which are bound to buttons. And so I'll need a new command, or I'll need a new command controller. So we'll do private final command Xbox controller. And then we'll attach that to port 0. And so this is how we can essentially map commands in our robot to buttons on the drive controller. So let's say we want to map something to the button A, right? So what we'll do here is every time we press A, we're going to run a new instant command, which is essentially going to reset our PID subsystem. Reset. And then we'll need the simple PID. So what this is going to do, oops, I can't do this. What this is going to do is every time the controller presses A, we're going to launch a new instant command, which essentially runs one function, and that function is this reset function. So every time we press A, we're just going to run it quickly, and then that's the end of that. Controller, let's say we want to map B, we're going to say .onTrue equals a new, oh, and I have to make a new command. So we're going to say run PID.java. And so we're going to make a new command here. And then I'm going to bring it up over here. And so the purpose of this command is to essentially change the PID controller. So there are a couple of ways that you can have command-based PID control. One of them is to have a PID controller within the command, and what it will do is it will, because we talked a little bit about this the first week, but a command lifecycle essentially follows 4 functions. So you have the init, the execute, the is finished, and the end, right? And so the PID controller can live within this, and you init it, you give it a target value, execute, you feed it the current value of the system that you're running. So if you're running the drivetrain, you'll be feeding it encoder values. Is finished is going to check the target value and the current state, and it will tell you whether or not you're close enough to be done. What this command does is it's sort of the second one, where your subsystem has the controller running in it, and you're just going to be changing the target output of that, right? So here we're going to need our subsystem. So we'll do PID, simple PID, PID, yeah. And then we will do, oops, this is the second time I've done that. And then we will do private double target, and then public run simple run PID, and then we'll do simple PID and then double target. Oh my goodness. There. My gosh. What are you talking about? Okay. So what we're going to do is we're going to say this dot. Are you kidding me? Okay. this dot target is equal to target actually spelled right, and this dot simple PID is equal to simple PID, also actually spelled right. And then we want to add our requirements, no, which is just our simple PID substance, right? So just like any other command, here we're going to override our init function. So we'll do initialize, and then on initialize we're just going to have our PID controller reset, and then here is our execute. So we'll override our execute, and then here we will have our simple PID subsystem dot set target to target. You can also put this in the initialize because you only need to set the target once, but I'm just going to do it in execute because I want to show you guys all the different cool functions that you can override. And then override public boolean is finished. And so this is the function. This is the function that essentially tells you whether or not your command is done. So what you would do is here you would say like, and this is just pseudocode, but if current position is within a tolerance of the target. So like let's say our target position is 1 and we're at 0.9. I mean, I think that's close enough so we can be done. I'm not going to nitpick over 0.1. Like that's good enough for me. But right now we're just going to return false because we just want this thing to run. And so we've got our new function. So we're going to say whenever we press B, we just want to run a new sample of this. So we'll do run PID. And we will say, let's go to 100, right? And so on A, we're going to reset our system, and then on B, we're going to set the new set point to 100. So let's simulate this, and hopefully it works, because that would not be the greatest. I just got to compile first. Cool. I'm going to open my sim GUI. And then I'm going to zoom in so that way you can actually see what's going on. Okay. So I attached command controller to joystick 1. So I'm going to attach my keyboard to joystick 1 so that way I can control the 4 buttons, or I guess only 2 buttons that I have. And then I am going to enable teleop. So the first thing that we will see is if we look at our network tables, and we look at Smart Dashboard, you'll see we've got, okay, well, that's supposed to be controller 1. It's under controller, whatever. But controller 1 has KI, KP, and KD. So I can edit these and set the PID controller to have that. So right now we're going to keep it at 1. We're going to keep it at 1. And then we can also plot our position and our target position. So if I zoom out, you'll see right now that they're overlapping. But if I reset the current position and if I reset the PID function, I'm going to make this bigger, right? Our current position drops to 0 instantly, and then it's going to try to get back to the target position, which is 5. And so it's trying to adjust for, hey, we're at 0 now, we're supposed to be at 5. Let's shoot up and overshoot to where we want to go. And so this obviously first tells me our KP is too high. And so what we can do is half this and see what happens, right? And so now that overshoot is not bad at all. What happens if we change this to like 100? Yeah, right. Something like that happens. So tuning that p-value is essentially the biggest step to doing this. And then, so let's change this back to 0.5, because while we did have a little bit of overshoot, we can actually use the KD value. That's too high. That's also too high. We can use the KD value to help dampen that oscillation. So we can keep, see, like right there, that's like perfect. That's what we want. We can keep this quick jump up to where we want to go, but we can use the KD to squish that oscillation down to where we want it to be. All right, so tuning these values just takes playing around with. This code is simulated. Obviously, when you're doing it in real time, you're going to have friction, you're going to have static, things like that. Not static. But you're going to have various things that's going to impede on your flow, right? So it just takes experience and time and things like that. So we're done with this code. Let's go back. That's essentially PID control. Let's get into more advanced control loops while we still have a little bit of time. So PID control, it works. You could use it for everything, but there's better things out there, right? So especially in FRC. And so this is where we get to motion profiling. And so what this does is you add velocity and acceleration into there. So now you have two more constraints that goes on top of your PID control function. So you have better control over what that curve looks like. So right here, you can see this is what we call a trapezoidal motion profile. So the velocity is broken up into, and I'll talk about this later, but the velocity is broken up into three phases. And so it just gives you a finer tune over what the profile looks like, and also it gives you better deceleration when you hit the target. So it, lessens the mechanical load on the system. You also have state space control. We don't do a whole lot of state space control. That's more advanced autonomous stuff. And then we have vendor-specific closed-loop controllers. I'm going to link some videos on these because I used some videos last year. And there's one mentor who's the mentor for, what team is it? The Orange City Gearheads. And he does a very, very good tutorial on vendor-specific closed-loop controllers. So I'll link that, because his is much longer than an hour. So yes, so trapezoidal motion profiling is Motion Magic, Rev Max Motion, the Profile PID controller. If you've heard of these, essentially what it is it's you plan a velocity profile that looks like a trapezoid. So it breaks the motion of your mechanism into three phases. You have the acceleration, the cruise velocity, and then the deceleration. And so what this does is the deceleration lessens the mechanical load on your system. It creates a much smoother trajectory. It's much more repeatable, and overall it just looks much better. So this is very good for like elevator systems and other things as well. So I've got a basic, let me bring up my profiled PID controller, right? And so essentially what it is you add two additional constraints onto the PID controller. You have your velocity and your acceleration. Motion Magic and Max Motion, which are both specific to CTRE and Rev, specifically. They both run on the motor controller, which is great for programming because you want to offload as much as you can from the RoboRio. And so what these two things do is you tune them in, like, let's say, because I've only used CTRE, I don't have much experience with Max Motion, but you tune the Motion Magic in the Phoenix tuner, and so you do all the work on the motor controller, and then the Rio just asks for values from the motor controller, and so it offloads a lot of that mathematical, like, intense computation, and speeds up your actual robot code while keeping it light and stuff like that. But I'm going to show you guys a little bit of the generic WPI Lib version of the trapezoid motion profiling, just in case you don't have CTRE or Rev. I don't know if that's a thing if you have your own custom motors, but yeah, this will run on the RoboRio. So let's pull up here. And I'm not going to try to redo it because that took way too much time. I'm going to just show you what it looks like. So here is a basic subsystem, and it's going to look very similar to what we did last time, except for one thing. Here in the PID controller, you have one additional parameter that you pass in, the constraints parameter. And so this is a trapezoid profile constraints. You give it your maximum velocity and your maximum acceleration, which I define right here in this constant file. So in this one, I've got a p-value of 4, a d-value of 0.4, and it's very similar tuning to the regular PID controller. But here you can say, well, I don't want to exceed 1, let's say you're doing meters per second, but you could do whatever you want. If you're working in raw encoder values, you can do like, X amount of rotations per second, and then you don't want to exceed, a set acceleration, right? And this is great for elevators that have very precarious things hanging off of them. You want to keep your acceleration low, but you still want to get up to a good amount of speed, right? So here you might say, like, I want a maximum velocity of 0.5 or acceleration of 0.5, but I can get up to 3 velocity, right? So you don't want to do very jarring movements, but you still want to be able to get to where you want to go quickly. So this just adds additional things onto your PID control loop. All right, and so this is how you would define it right here. And then same thing, I've got a position and a velocity and a set point. I'm publishing all my good stuff to the smart dashboard. And then this is something that we didn't talk about last time, which is tolerance. I did kind of talk about it, but it's like how good is good enough, right? So in this particular instance, I want a position tolerance of 0.01. So unless I'm within 0.01 units of my target, I don't want to stop. I want the PID controller to keep correcting. Here we have a velocity tolerance. So we can get to our position, but unless we're going under 0.02 units per second, I don't want to stop, because that might mean we hit and overshoot a little bit, and then we're still correcting. If we don't have this velocity tolerance, then we're just going to stop above, right? So we don't want that. And then our set goal is just the same thing, set the output target, set the set point. We've got our reset function, we've got our set goal function, and then here we've got our periodic. So we can live tune, and then this is just a fancy little function which essentially just checks for different values of PID. So what it will do is very similar to the last code. It's going to check out the network tables, see if there's a new value here, and then if there is, if there is, then we're just going to change those right here, right? So if any of these are, this is just a weird little thing. And then we're also going to be publishing our max velocity and acceleration right here. And then we're publishing our set point. And so I'm going to comment this out. Boop, boop. And then comment this back in. Right? So what we're doing is I'm going to simulate our velocity, and I'm going to simulate our position based off of that velocity. And so, what we're doing is we're calculating a new position with our profiled PID controller. So we're giving it our current position. It knows where it wants to go with this set point, and so this output is essentially where we want it to go. But we can also, calculate velocity based off of that. So this is what an ideal trapezoidal velocity profile is going to look like. So I'm going to simulate that and show it to you as soon as this builds. And it's the robot container is set up very similarly, where we have which one is this? This one. It's set up very similarly to where we just have our command Xbox controller, our buttons tied to different commands, which will set our goal to different target set points. We do not have we're not using this one. This is just another way to do it. So like, let's say our subsystem here, which it does, is in control of the PID controller. Instead of just creating a whole new function for changing the set point, what we can do is just run instant commands which run the set goal function to a particular position that we want to set it to. So let's bring up our sim GUI again. I want to make sure I'm 200%. Okay, whatever. So if I press one of the buttons that changes the set point, so like, I have to enable, whoops. So like right here, I set the set point to 2. So you can see here we have sort of like a weird looking S, and this green is our velocity. So I'm going to I'm going to decrease the maximum velocity, let's say 1, right? And then I'm going to increase the maximum acceleration to 2. So this tells our PID controller, hey, you can have a good acceleration, but I do not want you to go over 1 meters per second. So what looks like is we've got our velocity, which shoots up at the start, so we've got good acceleration, but we hit our maximum velocity of 1, so we're just cruising until we get to this point where we're pretty close, so then we start decelerating. And so what that shows you is you've got that nice acceleration at the beginning, which gets you up to speed, but then you also start slowing down when you reach your target so you don't overshoot, right? So the odds of overshooting with these are much smaller. And so, so we're going to get rid of this. But this is nice. What's actually going to look like in an actual system is, here I'm going to uncomment those and comment these. You're going to have damping, you're going to have resistance. There's a lot of external factors like friction that's going to happen. So you're not going to have that really tasty looking velocity profile. You're going to have something that looks more like a bell curve, if you're familiar with distributions. So let me bring up, I'll just show you. Right, so your velocity curve is going to look something like this. So this is a good example of what happens when you overshoot with a trapezoidal position. So you'll have your acceleration, and then when you hit your deceleration, you say, oh, I didn't decelerate fast enough, I went over. So now we have to accelerate again and level off. So this tells us, one, that our p-value is too much, so we can decrease that, resume it, and then see what happens when we actually enable teleop. Right, so our p-value, that's nice. We can increase d-value if we want to. That actually might be too high. But yeah, so this is the idea behind more advanced control schemes like the trapezoidal, is you have that it breaks it into 3 phases rather than just shooting right to the target. You're accelerating, you're cruising, and then you're decelerating. Be gone, right? I've got 1 minute, so I'm going to show this. All right, hold on 1 second. I've got some elevator code, which essentially simulates a trapezoidal motion profile on an elevator. And this will be on GitHub if you're interested. But what the subsystem looks like is you can simulate like DC motors. So like this is a Neo motor, your height, your carriage, your gear ratio. And I'm going to link a video, but all of this is really important for creating really smooth trajectory profiles. And so you can use your gear ratio, your motor, like max velocity and things like that, to get initial PID values to not have to worry about it. And then also in this code, I play around with the elevator feed forward. So like I said, what you would do is you would just drive your elevator up and then just let go and see just the right amount of voltage it would take to keep your elevator mechanism from dropping. And so you can add that. Get out of here. I'm not done talking. You can add that in when you set your velocity or your voltage to your motor. You can add that to reduce the amount of effort that the PID profile has to take into effect. And this is all just cool log stuff. But yeah, this will be on GitHub if you're interested. So like right here, our feed forward voltage, we just calculate it based on the desired place, and then we add it to our voltage. So that's all feed forward is. So here you can see a funny little elevator. We're going to turn on teleop, and we're going to move our elevator to a position. Right, so we've got a couple different set points that we can run through. Obviously, we need to tune our PID values because that is really slow. But this gives you a funny, I mean, it doesn't really look like an elevator. But yeah, it's just something to play around with. It's something to play around with to give you a good idea of how to do it before you start actually doing it, because it's going to take you a long time. But here are some good rules when, turning this on. Let's say you're doing an elevator, right? So the step 0, obviously, is validate the sensors that you're going to use and find their limits. So you want to verify the polarity of your encoder. So you want it to make sure that when you're going up, positive encoder values, going down negative. You want to convert to known units, right? So I recommend finding how many rotations it takes to get up to 1 meter or half a meter, and then just converting everything into meters. And then check mechanical limits. I have been to a couple competitions where someone, me, didn't check mechanical limits and broke something literally in the pits. So that was not fun, right? So just make sure it's safe. I do it in simulation first. Verify feed forward, right? So like I said, jog your elevator up, let it sit, give it just enough voltage with the controller to where you don't need to do it anymore at your K gravity. Set realistic constraints. Don't give it 100% of your max velocity and acceleration. I do it at 30%. I might have went up to 50 to 60 at competition, but I don't think, given a very small size constraint, you'll ever hit max velocity. Tune PID. I'll send you the video. He provides a really good Excel sheet to get very good guesses of PID values as well as other constraints that you can use. But tune P first, get minimal overshoot, and then add D. I don't think you'll ever have to touch I. And then graph and log everything, right? So record values, record the tuning process, because I guarantee that you're going to have to do it again and again and again and again. That was what we did last year. We would tune our elevator, and then we were like, oh, we have to make a small adjustment. Okay, well, now we have to retune it, right? So just make sure you document how that works. I'm going to stop the recording, and we can do a Q&A session. I'll post the link in the chat to the video. I recommend watching it because it's a great video.